How do we manage to improve our innovation capacity? How do we help complex industries to become creative? And how do we prepare students, especially engineering students, to develop breakthrough technologies or solutions? This seems to be a kind of impossible task. So we want to present to you the important advance that we have made in this direction, and we have developed a new approach called CK theory that is rooted in the creative power of modern math.
CK theory is a very powerful theory for discussing design phenomena.
What I think is interesting in CK theory is that you can describe it in multiple levels. You can think of it only as a simple interaction between two spaces, the K space and the C space.
And so far I can say that we have in our space division, but also in the transport division and others in the service division, we have already successfully achieved some CK sessions and exercises.
Our findings seemed to have parallels in CK theory. So we were able to see a relationship between both the theoretical predictions and what we were getting experimentally.
Learning CK theory is a valuable asset for engineers, as it is a very powerful framework to understand and to develop creativity in engineering projects.
Let's get back to the essence of the problem. What is creativity? There have been a lot of studies about creativity, but they have sent us one simple message. Creativity or creative thinking is resisting to some fixation effect. What is a fixation effect? It's a set of rules that we have in our mind and we have difficulty to change or to make it evolve. To understand what are fixation effects, let's take some very practical examples. For instance, optical illusions. Please look at these two lines. Which one seems to you the longest? Actually, both lines have the same length. So, it's our mind that have decided that the vertical line was longer than the horizontal one. This is a fixation effect. This first fixation effect comes from our human senses, optical illusions. Let's take another test. Please try to make a square by moving only one match. The surprise here comes from the word square. A square can be also a square number, 4 in this case. The fixation effect came from the fact that we didn't use a knowledge that we already have, the existence of squared numbers. Therefore, to be creative is to be able to resist to a fixation effect. How? By expanding our ideas and thoughts. And there are two types of expansions. In the first one, we give a different meaning to an existing object. We interpret differently the signification of the object. The second one is more ambitious. We want to create a new object that was unknown at the beginning of the process, and we want this new object to have some desired properties. So now we have understood what is creative thinking. We know that we need expansions. So where do we find methods that allow us to systematize the production of expansions and hopefully to create them without nonsense of contradiction? The good surprise is that such type of methods exist in modern mathematics. So where do we find expansion examples in mathematics? Not necessarily standard ones, but in mathematics that have been developed in the modern era. The first example came from a mathematician called Joseph Bertrand, which showed that we could answer in a surprising way a rather simple and well-formulated problem. Let's consider a circle and the equilateral triangle within the circle. The problem is to evaluate the probability for which a string randomly distributed could have a length that is longer than the side of the triangle. This seems well-formulated problem, and it should have one exact solution. The surprise came that there is an expansion. There is some notion that will have different interpretations, and the creative mind should think, where is this notion which has several interpretations? The issue is in randomly distributed string. Because if we want to distribute a string, we can take several cases. We can define the string by its middle. In that case, we have one type of random distribution. If we define the string by one of the intersection points with a circle, we have another type of random distribution. And if finally we define a string by its direction, we have another random distribution. And the surprise is that each one of these cases gives a different value. All are exact, but they are all different. But let's take another example that will bring us a step forward. There is a famous case in mathematics called complex numbers. These numbers have a strange property. Their square is negative. How can we think of a squared number which is negative? Well, the answer is that these numbers are designed, and they are innovatively designed in order to reach the desired property, which is the negative square. Very accurately, mathematicians called these numbers imaginary. But the problem is that it is not important for these numbers to be imaginary if we can use them, if we can have them as very efficient tools. This is the essence of creative design. We will invent something for the desired properties. And this is what mathematicians have done. Well, now we have seen two examples of expansions in mathematics. But what would be even more interesting is, can we find some general technique or method that we could use to produce expansions in a systematic and rational way? The surprise, and the good surprise, is there is such method. It was discovered by Paul Cohen, a mathematician, in the middle of the 60s. Paul Cohen showed that we could design sets of numbers with an infinite size, but this size can be as big as the designer wants. So he gave a general method for designing infinite sets. This method is called forcing. We can force sets to have the desired properties. Forcing is a very, very technical development in modern maths. But let's only keep in mind the main ideas of forcing. The first idea is we provoke expansion, the creation of a new object, by step adding properties, unexpected properties, so that suddenly a new object appears. The second idea or principle of forcing is that we can select these attributes, these strange attributes, so that we get the properties we want. Now, what is the crucial consequence of all that? Well, a crucial message of forcing is that creating creative things cannot be obtained by deducing them from already existing knowledge. We have to intentionally force the process. Why? Because at the beginning of this process, that things we wanted to create is undecidable. It will be decidable only when these things will be designed. Now we have a better knowledge of the creative process. We know that we have to begin by an undecidable proposition about a thing. But we are not lost. We know how to do. We know that we have to expand this definition by a step-by-step adding of attributes, and we know that we have to carefully select these attributes to get the desired properties. Forcing was an amazing change in the world of mathematics. It introduced the idea of design in the mathematical world. What we have done is to adapt forcing, and we have developed a theory called CK theory that extends forcing in the world of things, objects, technologies in the real world. So let us present CK theory with an example. The departure point, we know it, is an undecidable object. So let's take the case of a flying boat. Most of us never met flying boats, but yet this doesn't prove that flying boats do not exist. So what can we do? We know the process. We have to add attributes to the idea of flying boats so that we progressively expand the process toward the generation of a new object. What do we know about boats? What do we know about flying? These are the notions that we are going to interpret, and interpret in a wide way. Let's consider flying. We can fly with wings, delta wings, for example, or with like a balloon. Now we can begin to expand the idea of flying boats with two different directions, flying boats with delta wings and flying boats like balloons. We are developing a space, an imaginary space, where new things are progressively appearing. We can call this space the C space, the concept space. But from where did we know that there are wings and there are balloons? From another space that we call the knowledge space. So this knowledge space provides us with new attributes that we can use in the concept space. The core property of CK theory is precisely what happens when we go from C to K and K to C. Let's take the path from K to C. To expand in the C space, we need new attributes. So the more knowledge we have, the more we are able to generate new directions, new conceptual directions in the C space. But let's take the other way around, from C to K. In that case, it is the fact that we develop new attributes for the things we design that will bring us to expand our knowledge. We can go to new experts, we can do research, we can activate new ways to acquire knowledge. And in our example, if we think of a boat as a flying fish in the sea space, we are now stimulated to go to places where we can learn about flying fishes. And what we are going to find is that in the flying fish, the fin is also a wing. So our knowledge about wings will change, and new attributes about wings will appear that we will transfer in the sea space to generate new designs. Thus, CK theory offers us a step-by-step process to design creative things. But also, it unveils the mystery of creation, its strange and odd aspects. These odd aspects came from a long tradition that makes us separate two things. On one side, we think about creativity as generating, in disorder, new ideas, like in brainstorming, for example. But we think that this is different from research, rational investigation processes to create knowledge. What shows the CK theory is that creative design is precisely the interplay between the generation of strange ideas and the expansion and the rational expansion of knowledge. How is this? Finally, the more we have increased our knowledge, the more we are able to generate crazy ideas. But these crazy ideas, again, are a way to invite us to develop knowledge in unexpected directions. This was very difficult to think before we developed CK theory. So let's take a simple example of CK theory to show how CK theory can help to design a creative object. The problem is to design a camping chair. What do we want about innovative camping chairs? We want them to be lighter, as light as possible, and we want them to be very easy to pack. So classic camping chairs can be found everywhere, and there are different ones according to the different types of design strategies that has been used. So let's consider now a very strange camping chair. This one. It's a very simple belt, and it's a carpet. It's a combination of both. And the combination of both allows you to sit very comfortable and very easily during your camping moments. The surprise is that it's not a chair, or that you don't think of it as a chair. But CK theory would have helped you to design this strange thing. How? Let's take the standard knowledge that we have about camping chairs. We know they have a lot of different components, but especially the design effort have been made on how the chair is related to the earth, the type of legs. Now, if we consider in the sea space, we will have a different meaning and interpretation of legs. Legs could be 1, 2, 3, or no legs. A chair with no legs, strange. But a chair with no legs is a very interesting object to think about it, because it invites us to create knowledge. Knowledge on what? How do you sit on the earth? Oh, it's not so simple to sit on the earth. So we are going to study how you sit on the earth. And what do we find? We find that the equilibria, sitting equilibria on earth, is very interesting and very difficult. So if you sit on the earth, what is interesting is to give you a media that helps you to sit on the earth. So the new camping chair is a camping chair with no legs, and that helps you to sit on the earth. We are not far from the very nice object we have showed you. And it's only the interplay between the crazy idea, no legs, in the sea space, and the acquired knowledge. How do you sit on the floor on the earth that brings you to this very interesting and strange chair. Finally, what have we done with CK theory? We have developed an expansion machine that allows you to realize both expansions that we have defined in the beginning. One, increase your capacity to interpret differently and give different meanings to the same notion. And the other is to be able to generate, by a step-by-step process, a real new object, and to have increased simultaneously your knowledge. Thus, CK theory offers a systematic, step-by-step method that can help students to develop new breakthrough things, breakthrough techniques, breakthrough solutions. But two ideas are important here. One, they are helped to control the rationale of their developments. They can control the degree of innovation they want to reach, and also they can bring back to their professors the explanation of the different design paths they have been following. What is good for students is of paramount value in industrial contexts, for people which are in charge of leading innovative projects in R&D departments or in special teams for new technologies. Three different types of impact have been reached with CK theory. The first one is we can improve the capacity of innovation of a design team. The second one is that we can increase the potential and the concepts that have been developed. The third one is not the least one, it is of paramount importance also, is we can improve the quality of the collective work in these innovative teams, because CK theory helps to clarify the complex interplay between C and K in the design process. And this helps people to communicate and to understand themselves. Where are we now? In the academic world, CK theory has received good recognition, and we have now set up an international group within the design society called Design Theory Interest Group that is developing and advancing in the direction opened by this new breakthrough in design theory. In the industrial world, we had great impacts in several world-class industries which are now sponsoring a new chair at Mines ParisTech in order to improve, develop and strengthen the research in this field, and thanks to them we came now to speak to you and to present our work.